We are going to talk about 3D geometry and VSEPR theory. So VSEPR theory is the theory we use to predict the 3D geometry of a molecule. So there are a lot of different shapes out there. There's 5 main ones that we're going to look at, even though there are others. So the first one is bent. Then we have linear. Let's see, we've got trigonal, planar, and we also have trigonal pyramidal. Okay? And then another really popular one is tetrahedral. So these are 3D. That means they have to show shape from every direction, not just flat. They are based off of the electron dot structures, but they are very different things. So bent looks like this. A bent molecule is when you have something like this. So we've got a central atom and then 2 of them that are attached. There is often a lone pair or maybe 2 lone pairs on top, all right? And these a lone pair of electrons. We only care about lone pairs on the central atom, okay? Central atom, that's it. We don't care for this if there's lone pairs on the surrounding atoms. So there's always a central atom, and figuring out what your central atom is super important. So we only care about lone pairs on the central atom. Okay, let me keep going with my drawing, but I'm going to erase that and give myself some more room. A linear molecule looks like this. Kind of looks like a barbell. It might even have 3, might even have 4. Either way, these are all linear. They make a straight line. They have no lone pairs. None, okay? Trigonal planar. Trigonal planar has a central atom in the middle. Maybe it would help if I made my central atom a different color. Okay, central atom. And tri means 3, so it's going to have 3 atoms around it, evenly spaced out. Also, no lone pair. Trigonal pyramidal. Trigonal pyramidal has a central atom, and then trig again means 3. It's going to have 1 atom going out to the side, 1 coming forward, which we draw with a solid wedge, and 1 going backward, which we draw with a dashed wedge. It also has a lone pair on top, just like bent did. So do you see how we get this kind of V-shaped situation? That happens whenever there's a lone pair. So this has a lone pair. Do I need to write that? I'll write that. Lone pair. Okay, and our final one is tetrahedral. Tetrahedral also has a central atom. Tetra means 4. It's got 1, 2, 3, 4. 1 going backwards. No lone pairs. No lone pair. So these are the major ones. Now, let's look at how you figure out when to use this. Okay, let's start with water. Water is H2O. Our goal is to draw the 3D geometry. To do that, we have to draw the Lewis dot structure first. Okay? Lewis dot has to draw first, 3D doesn't. Lewis dot shows all the electrons. 3D geometry does not. It does not show electrons. It only shows shape. So let's talk about water. The central atom in water is going to be our oxygen. It goes in the middle. We're going to ask ourselves how many valence electrons it has. It has 6 valence electrons. Hydrogen has 1 valence electron each. There are 2 hydrogens. They're going to go on either side. Oxygen has 6 valence electrons. Because there's 2 hydrogens, 2 of them have to go to the hydrogens, right? Has to. Hydrogens each have 1 valence electron. Let me recolor this. Okay? So I have now used 2 of the 6 valence electrons. That means there are 4 left. 1, 2, 3, 4. You are going to go look at your reference sheet. You have a reference sheet. It lists all the shapes. And on that reference sheet is this nice thing we wrote up that talks about the A, the X, and the E notation. And the A represents the number of central atoms. So you can see here we have 1, the oxygen. How many surrounding atoms do we have? We have 2. So our X is 2. The E represents lone pairs on the central atom. There's 1, 2. 2. If you go and look, you will see that the only shape that has this exact notation is bent. So the name of this is bent. And to draw that geometry, we draw the O in the middle, and then the hydrogens are pointing down because it's creating a bent shape. The reason it does that is because these electron pairs are up there pushing the hydrogens down. Now, when we draw the 3D geometry, we don't usually draw the lone pairs, but it's important that you draw your hydrogens pointing down because those lone pairs are making that happen. Okay, let's try another one. Let's try BF3. We're going to start with the Lewis dot. Actually, we're going to start with valence electrons. How many valence electrons does boron have? It's got 3. Fluorine has 7. And there's 3 fluorines. So boron is going to be our central atom. It has 3 valence electrons. That works very well because guess how many fluorines we have? 1, 2, 3. Fluorine has 7 valence electrons. Of those 7, 1 of them has to go bond with a boron. That leaves 6, which creates 3 lone pairs. That's going to happen on all of our fluorines. So let's talk about our AXE. How many central atoms do we have here? 1. Boron is in the center. How many surrounding atoms do we have? 3. How many lone pairs on boron? Oops, I missed some of these. None. None. All of the electrons on boron are bonded. So there are no lone pairs. None. So our E is 0. So what shape fits the bill? What allows for 1 central with 3 surrounding? The answer, my friend, is trigonal planar. Trigonal planar has no lone pairs. So we're going to have our B in the middle with an F, an F, and an F. And they're going to be spaced out in such a way that they create a triangle, so they're as far away as possible from each other. All right, let's try another one. Let's try CH2 Br2. Okay, what's going in the middle? Carbon. Carbon has 4 valence electrons. Hydrogen has 1 each. Bromine has 7 each. I know that because it's a halogen. So carbon's going to go in the middle. Carbon has 4 valence electrons, and carbon does not allow lone pairs. So that means they all need to be bonded. Well, there's 2 hydrogens and 2 bromines. That's 4, which means each one of carbon's valence electrons is going to go to one of those. So an H, a Br, and a Br. Now, hydrogen only has one valence electron, so it's going to bond like that with the carbon. Bromine has 7. One of them's going to bond with the carbon, then that leaves 6, which creates 3 lone pairs. So overall, let's look at this AXE situation. How many central atoms do we have? There's just one. How many surrounding do we have? 4. How many lone pairs on carbon? None. So this shape, if you go look that up, is tetrahedral. Our carbon's in the middle. In tetrahedral, one goes up, one goes to the side, one comes out forward, and one goes to the back. Tetrahedral. Do you want me to keep going? Okay, I'll do 2 more pretty quick. I'm going to keep that same kind of setup going. What if we have HCN? Okay, hydrogen has 1 valence electron. Carbon has 4. Nitrogen has 5. Carbon is going to be in the center. It has 4 valence electrons, and it's going to have this hydrogen and this nitrogen. And hydrogen can only handle 1, right? So carbon can only use 1 of its 4 for nitrogen, or for hydrogen. No lone pairs allowed, which means its other 3 have to go to nitrogen, have to. So nitrogen needs to use 3 of its 5 for that carbon, which means it's got a lone pair left over because it needs a grand total of 5. If we go through our AXE, we have 1 central, so 1. Surrounding is 2, and how many lone pairs on carbon? None. This is linear, and we just draw it as an H, a C, and an N. In 3D geometry, we don't show triple bonds or double bonds usually, so you don't need to draw that. It's just showing the shape, just that it's linear. Our Lewis dot structure shows us that we have a triple bond right here. Okay, one more. Let's do NH3. Okay, nitrogen again. Nitrogen has 5 valence electrons. Hydrogen has 1. So nitrogen is going to be in the center, and it's got 5 valence electrons. 3 of those need to go to the hydrogens, which leaves 2 left over to get our total of 5. There are 3 hydrogens. Hydrogen only has 1 valence electron, so it looks like this. All right, A, X, E. There is 1 central atom, nitrogen. There are 3 surrounding. And how many lone pairs on our central atom? Right here, there's 1. Look on that reference sheet you've got. The only shape that lines up to this is trigonal pyramidal. It looks like this. Your nitrogen, a hydrogen coming out, a hydrogen coming forward, and a hydrogen going to the back. That's pushing them down into a pyramid shape, like a little tripod. Okay. I think that's about it. So, as a quick reiteration, I think what we really need to know is that when you draw these are called Lewis dot structures. This over here is called the 3D geometry. But even though you're only ultimately looking for 3D geometry, you need to go through the Lewis dot to figure it out. Because if you don't draw your Lewis dot structures, then you won't recognize when you've got a lone pair. And the lone pair makes a big difference. So like if we go back to the very top, when we were drawing this, see the only difference between trigonal planar and trigonal pyramidal is the lone pair, right? Like they both have 3 surrounding with 1 central. The only difference is this lone pair. So it really matters. Same with bent. If you come look at bent has 2 surrounding, just like this linear, with 1 in the middle. The difference is the lone pair. So unless you can visualize that in your head, you need to draw the Lewis dot to get to the 3D geometry. Okay, I hope that clears things up and makes sense. All right, you guys are the best. Bye.